Welcome, pre-calc honor students. Here are the logarithmic functions. First, we're going to start off with the definition of a common logarithm, log base 10. This is the one that's on your calculator. It's very easy to find. Common log of x equals a if and only if 10 to the a equals x. So it's this missing power in between here. So when we look at the common log of 100, that's equal to 2. Because 10 squared equals 100. And the common log of 1,000,000, otherwise known as 10 to the 6th, will equal 6. Because 10 to the 6th equals 1,000,000. Okay, let's look at an application of this right away. Decibel levels. Two loud stereos are playing the same music simultaneously at 80 decibels each. What is the decibel level of the combined sound? And by how many decibels does this increase? Well, here's the formula, and you don't have to memorize this formula. This would be given to you. It's an application problem. Intensity, the decibel level of an intensity level I is equal to 10 times the log of the intensity over the I naught, where this I naught is the intensity of barely audible sound. So when you look at this problem, 80 decibels, the new intensity, is two stereos. The intensity of two stereos is 80 decibels plus 80 decibels is 160 decibels. That's what you might think, but decibel level doesn't work that way. First of all, the decibel level for one stereo is 10 times the log of the initial intensity, the intensity over the initial intensity. So when you have decibel level of 80, we get that when we change this over to an exponential equation, we have I over I naught equals 10 to the 8th. Or the intensity of one speaker is 10 to the 8th times the intensity of barely audible sound. Now, what does this mean when we have two speakers? With two speakers, two stereos, the actual intensity level for two is twice the intensity level for one, which was twice times 10 to the 8th over initial intensity. Now let's put this in our decibel equation, which is 10 times the common log of this intensity for two speakers over the initial intensity. So we get 10 times the common log of twice 10 to the 8th initial intensity over initial intensity. These initial intensities cancel. You put this in your calculator, 2 times 10 to the 8th, and let's see what we get. Okay, on my calculator, I get 83.0103. So it only went up by 3 decibels, because this is on a logarithmic scale. Also notice here I put down some of the shortcuts you can find in your calculator. If you use diamond 7, that's how you can get to the log key, the log key. And this EE is for scientific notation. So to put in 1 times 10 to the 8th here really quick, I just put in 1E8. So I could also just put in 2E8. That would have been 2 times 10 to the 8th power. Okay? Moving right along. Now, general logarithms. You don't have to stick to base 10. Log base b of x equals a if and only if b to the a equals x. The log is the power you raise b to in order to get a. So it's this missing power idea. Let's apply that in these examples now. Log base 3 of 9 equals 2, because 3 to the 2 equals 9. See how 2 is the missing power between 3 and 9. Log base 3 of 9 does not mean divide 9 by 3. It's log base 3 of 9. Notice how I'm speaking it now. Log base 3 of 9. Log base 2 of 8 equals 3 because 2 cubed equals 8. Log base 5 of 625 equals 4 because 5 to the 4th equals 625. Now, this one gets a little tricky. Log base 7 of 1 over the cube root of 49. It's kind of hard to see this, so you can just start off by saying it equals x, and then say that's because 7 to the x equals 1 over the cube root of 49. And now try and rewrite both sides as powers of the same base. 49 is 7 squared. A cube root is a 1/3 power, so this is 7 to the 2/3. So 7 to the x equals 7 to the negative 2/3. So if 7 to the x equals 7 to the negative 2/3, ergo x equals negative 2/3. So there's three ideas here: the negative, the squaring, the 2/3. So that basically you've taken 7, and the missing power is to invert it. That's a negative 1 power. Square it, that gives you the 49, and the 1/3 power gives you the cube root. Now, natural logarithms are log base e. Normally we don't actually write log base e. We use a shorthand of lnx, log natural, or log base e. So let's try then some of these. We're going to figure out 10 to the x equals 75 by changing this into x equals the log base 10 of 75, which we just know as common log of 75. And you can put this on your calculator. You go second, go diamond 7 to get log, and 75, and there's your nearest hundredth would be 1.88. And then for e to the x equals 75, x equals the log base e of 75. You don't have to write out that step. If you can see, that just goes right to natural log of 75. And the natural log of 75 is 4.32. Okay? Now here's a little graphical demonstration of the logarithms, and we'll do this up on GeoGebra. Here's our GeoGebra. And here you can see I've taken that exponential thing with sliders that we had before. And remember how we changed the slider for the y-intercept and so forth? Well, I want to keep the y-intercept at 1 to just look at exponential functions with a coefficient of 1 in front here at 2 to the x. And then we can slide the base here. And as you make the base bigger, you can see you make the exponential functions more steep. And it actually makes the logarithm function more shallow because it's the mirror image. And notice, let's compare some of these. With the typical y equals 2 to the x log exponential function, the inverse is log base 2 of x. When we start cranking up this till maybe base e, which is about 2.8, that's close to your natural log function down here. And notice that the common log, we have to go way up here to base 10. And the common log is very flat then. You have to go all the way up to 10 to get up to 1, and 100 to get up to 2. So let's return this to 2 and get back to our main screen. And now we can actually annotate this a little bit in terms of some of the key ideas on this function. I had to stop at the log base 2 function because in purple here we've got the original function y equals 2 to the x, and it has a domain of all reals, but its range is y strictly greater than 0. Not equal to 0, greater than 0. We have a horizontal asymptote at y equals 0. Now when we look at the inverse function, it ends up being y equals log base 2 of x. And its domain is x greater than 0, because that whole flipping of inverse functions. And the range is all reals. And notice it has a vertical asymptote at x equals 0, compared to the original exponential function, which had a horizontal asymptote at y equals 0. So even that gets flipped as well. And the points are flipping as well, as we saw. 2 goes to 4 on the exponential function, and that becomes the point 4 comma 2 on the inverse function. All right, at this point, that's it for the notes. And you can stop here and start the homework if you want. I'm just going to run through a few more examples if you want a few more examples. Let's write this in exponential form. Log base 4 of 8 equals 1.5. Well, in exponential form, that means 4 to the 1.5 equals 8. Just change it from logarithmic form to exponential form. Now we're going to find all these logs sans calculatrix. That means without a calculator. So this equals 2, because 6 squared equals 36. So I'm imagining the power that goes in between these two. Now this one's a little trickier. To get from 36 to 6, you have to take a square root, which is a 1/2 power. So log base 36 of 6 is a half, because 36 to the 1/2 equals 6. Log base 6 of 6 square root is 6. Well, let's see if we can't write the inside as 1 power of 6. This is 6 to the first times 6 to the half, or the log base 6 of 6 to the 1.5 or 3/2 power. So we're going to get 3/2 for this. And this is one of the rules of logs we're going to develop, that if you can write it as the log base b of b to the x, that will just be x, because these are inverse functions of each other. Now this one gets really tricky, so another technique is to say, well, let's let it equal x and rearrange it, and say 6 to the x equals the cube root of a sixth, and then start writing both sides as a power of 6. So this is the cube root of 6 to the -1 power, so 6 to the x equals 6 to the -1/3 power. Therefore we get x equals -1/3. -1/3. Now again, solve some of these without a calculator. Log base 6 of log base 2 of x equals 1. Well, we can peel away the layers one at a time. So change just this outer much. Think of this as just some big blob. And so that means 1 is the missing power between these two. So 6 to the 1 equals that big blob. And the big blob is the log base 2 of x. So you get 6 equals the log base 2 of x. And now rearrange this. So a log is the missing power. The 6 is the missing power between these two things. So 2 to the 6th equals x. So we get x equals, one of my favorite numbers, 64. Now for this one, think of it as the log base e of x minus 2 equals 1, and then rearrange it. So that becomes e to the 1 equals x minus 2, or 2 plus e equals x. So that's what's set up here. Use e if necessary. That's the exact answer, e plus 2. Didn't ask us to calculate, so let's just stop at that point. And lastly, common log of x, all quantities squared, equals 4. Well, we can start by taking the square root of both sides. So we get the absolute value of the common log of x equals 2. So the common log of x equals plus or minus 2. Now you might think of throwing out one of these answers. No, the restriction is that you can't take the log of a negative number. This is log set equal to a negative number. So you have the common log of x equals 2, or the common log of x equals -2. So when you rearrange it, remember this is log base 10, so this becomes x equals 10 squared, or x equals 10 to the -2, and then we get x equals 100, or x equals 100th for your two answers. Flange out.